Coming to the arithmetic instructions of 8085, we have these 18 instructions including addition, subtraction, incrementing, decrementing, negating, that is complementing, compare, CMP. Then 9, 10 will be multiply and sign multiplication. Similarly 11, 12 will be division and sign division. This is decimal adjust accumulator. This is decimal adjust accumulator after subtraction. And these four are very interesting. We have ASCII adjust after addition, ASCII adjust after subtraction, ASCII adjust after division, and ASCII adjust after multiplication. So let them discuss one by one. First is add. We have already studied the add command in 8085, but the difference in between 8085 and 8086 add instruction is that in 8085 we need to have only the use only one operand, because the second operand is by default the accumulator, but not in the 8086. In 8086 we need to define two operands. The operand can be defined as a destination and the source. So the operands may be register or memory combination, memory or register combination, register and register both, memory and immediate both, and register and immediate. But these operands cannot be both memory and memory. So the source and destination cannot both be memory. At least one have to be either register or memory or immediate data. The algorithm for this addition is operand 1, that means destination will be destination plus the source. So for example, I want to add 05 with 03, that means 05 is moved into AL register first, then immediately 03 will be added to this AL. So the answer will be 05 plus 03, that is 08. Similarly, ADCs stands for add with carry. These operands are same. Algorithm will be slightly different. It will be there will be addition of 1 if the carry flag is 1. If carry flag is 0, then it is by default 0. So for example, we have 5, we want to add 5 plus 3 along with the carry. So this 5 we first move into AL, and this 3 immediately is added to the contents of AL. So that will be 5 plus 3 plus, we have assumed that carry flag is 1. So when carry flag is 1, that means this 5 plus 3 plus 1, that will be 9. If carry flag is 0, then this 5 plus 3 plus carry flag 0, that means the answer will now be 08. But if carry flag is set, that means the answer is 9. So this 1 is added if the carry flag is 1, otherwise it is not added. Subtraction is similar, the operands are similar. The algorithm is slightly different because instead of addition we need to subtract now. The command is the example, you can say that we want to subtract 5 and 3, then 5 minus 3, the answer will be 2, and 3 immediately subtracted from the contents of AL. Again, we need to mention here that source and destination cannot be both memory location. So the source and destination, they both cannot be memory. Either one has to be register or memory or immediate, but they both cannot be memory. Subtract with borrow. The operands are same. Algorithm is again the different is that the operand 1 minus operand 2, and the result is also subtracted with 1. That one is for borrow. If borrow flag, any carry flag is 1, then only this will be added. So suppose in this example we have carry flag set is equals to 1, that means by default contents are having a borrow. That means 5 minus 3 will be 2, and then 1 carry flag will be, or borrow flag will be subtracted, so the answer will be 1. Next is incrementing. Increment destination. So as it need only 2 operands, it may have a register or it may have a memory. Algorithm will be simply operand will be operand plus 1. So if we want to add increment the content of AL, then suppose 5 is moved into AL, then if we increment AL, then by default AL will be 6. carry flag will be same, but other flags are changed. We need to check what are the different flags, what are the flags latest value. Similarly, the decrement, it is similar to increment, operand either register or a memory. Operand will be operand -1, that means destination will now be destination -1. So if we want to subtract in decrement the quantity which is available in AL, suppose AL is 5, then if we decrement AL, then the AL value will be 4. Again, CF is same, rest all flags are affected. We need to check all values of the flags other than CF, because CF, if it is set, then it will be set after the command, or if it is reset, then it will be reset after the command. Negate, it is new operation, but again, negate destination, that means only one operand is required. Operand, that means destination will now become the destination's 2's complement. So for example, if we want to calculate negate the content present in the accumulator in the AL register, for example AL is 5, that means 0 0 0 0, and 5 that means 0 1 0 1. So if we want to calculate 2's complement, then first we have to calculate its 1's complement. So we'll subtract it from 1. So this will be 1 1 1 1, this will be 1, this will be 0, this will be 1, this will be 0, sorry. Now we add 1 to get the 2's complement. So this will be 1, this will be 1, this will be 0, this will be 1, and they all are 1. So these 4 will be F, and these 4 will be B. So the operation, the contents after the negate operation, for 5, the content will now be FB. Compare, the next is compare. We can have these 5 combinations: destination with source, compared destination with source. Algorithm will be operand 1 minus operand 2, but the thing is that we do not store the result in any of the destination or the source register or a memory location or immediately. We do not store the result. We are only focusing on the result, whether it is positive or negative or same. So for example, AL will have 505 and BL will be 04, and if we compare AL with BL, then AL will be 05, BL will be 04. There is no change. But what are the changes that will occur after CMP? That will be given by the flags. What are the different flags? Sign, 0, carry, parity. So we mainly focus these 4 flags, whether the data after the CMP operation is changed in these operations, in these flags or not. We mainly follow these 3 flags: sign, 0, and carry. We do not bother about the parity, because with this compare we either check positive result or negative result or 0. So 0, positive or negative can be given by this or this, and 0 result will be given by this flag. So we mainly focus on the results of these flags. Now in 8085 we do not have multiply. We have to create some algorithms to multiply the 2 digits, but this 8086 processor has a separate multiply command. The operands are registered in memory, so if we want to multiply, then it will be simply MUL comma destination. The destination could be no, it's not like that. Let's see the algorithm first. Algorithm will be when operand is a byte, that means if it is an 8-bit operation, then the AX will be AL into operand. So one of the operand is by default AL, assumed to be AL, and when the operand is 16-bit word or 2-byte word, then the result is available in the combination of DX and AX, these 2 16-bit registers, and this will be AX multiply the operand which we give. So MUL comma source, if we want to supply, then for example MOV AL comma 02, that means 02 is moved to AL, and 04 is moved into BL. Now if we want to multiply this AL and BL, then the result will by default stored in AX, and that will be what? The first one, that is AL, multiply with BL, that is the another operand. So this BL, that is 4, multiply with 2, will get 8. Flags we need to check. Next is IMUL, that means signed multiplication. Operands are classified as register or memory. Again it is same. When it's a byte, we need to check the result in AX, and it is like AL into operand. And when it's a word, that means 16-bit data, then we need to check the result from these two combination of the registers. So for example, I want to multiply -2 with -4. So the result will be stored in AX because it's an 8-bit data, and the result will be obviously 8. -2 and -4 will be -8. No, it's plus. Division. Next command is division. It is similar to the multiply, register and memory. Algorithm is same. AL will become AX divided by operand, and AH will be the remainder. If the remainder is available, then it will be stored in AH after the division. Similarly, if it is a 16-bit word, then the operand will be available in DX. DX into AX divided by operand, and that will be stored in AX, and the DX after the operation will give you the remainder. For example, it 0008 is moved into AX. Now we want to divide 0008 with 04. Then what will be the result? It's simply 8 divided by 4, that is 2. So 2 will be stored in AL. AL will store the result. This will be the result, and AH will give you the remainder. In that case, 8 divided by 4 has 2 quotient and 0 remainder, so the remainder that is stored in AH, that will be 00. Similarly, the data can be manipulated for the 16-bit operation also. Signed division, that is IDIV. Operands we can classify in register and memory. It is similar, but the data we use in signed number. So the first operand, that will be a signed number -8, and the other operand is 4. It's a positive one. So when we divide -8 with 4, we get -2 is the result, and 00 is the carry. So carry will be stored in AH, and number, that is the quotient, will be stored in AL. DAA, we know that. What is DAA? DAA is nothing but the decimal adjust accumulator. So if there is a number after addition we get more than 9, then we'll add 6. If it is less than 9, then simply the number will be same. So if we add 5, 8 and 3, 5, the result has to be 5 plus 8, that means 3, and 5 plus 1, 6, 5 plus 8, 13, 3, then 1, 5 plus 1, 6, and 3, 9. So the result will be 93. But if we add these two data using this add CL comma add AL comma CL, that means AL will be 8D. 8D because these two numbers are considered as hexadecimal numbers. So if the addition, we add these two numbers in hexadecimal fashion, we'll get 8D. But we want to have the result in BCD numbers. BCD does not have any number other than 0 and 9, 0 to 9. So this D, that means it is greater than 6. When it is it's greater than 9. When it's greater than 9, we need to add 6. So 8D will be added with this 6 to get the result 93. If in this case a carry will be coming, then the carry flag is set. Otherwise there is no need to set the carry. So in that case we need to check what are the flags that are affected. Next is decimal adjust after BCD subtraction. Now 8085 does not have any such command. We need to have a program if we want to calculate the decimal subtraction, but in 8086 we have this particular thing. So operand is same, there is no operand. DAS, that means by default the content present in the accumulator. The AL, that means low or byte, will be checked whether it is a BCD number or not. If it is a BCD number, then it's okay. If it is not, then we need to check it nibble by nibble. So if low nibble is greater than 9, we need to subtract 6, and if it's greater than 9 f, that means we need to subtract 60. So let's take an example. 86 and 57, they both are subtracted, so the result is 27. No, it's basically 2f. It's not 27, actually it's 2f. Typing mistake, there is a typing mistake. It is basically AL is 2f. So when we add 2f, this is not a complete BCD number. Auxiliary flag is 1, so we need to subtract this 0, 6, because it is greater than 9. This f is greater than 9, so we need to subtract. So 2f minus 6, that means 29. 29 will be the answer, and carry flag in this case is 0. In the other example, if we want to subtract 49 and 72, then the result will be D7 along with a borrow. As it is greater than 9f, D7 is greater than 9f, so we need to subtract 60. So if we subtract D7 and 60, we'll get the result 77, and as carry flag is set 1, that means it is indicating the borrow. So the number available in AL is actually less than the number from which we are subtracting. Sky adjust after addition. Very interesting. See, if if the low nibble of AL is greater than 9, that means we'll simply add 6 and we increment AH to 1. Auxiliary flag is 1 and carry flag is 1. Else there is no change in the flags. Let's take an example. For example, AX will be 0005. That means AH will be 0 and AL will be 5. Now if we move 06 into the BH register, then BH will be 5. And if we add these two, that means AL and BH will be added, then the result will be what? The result will be 6 plus 5 and 11. 11, that means 0B. But the result after AAA will not be 0B. It will become 01 and 01. Why? Because it is basically greater than 9. So we'll add 6. We'll get 1. And we'll get 1. Similarly, AH is incremented. So AH is 0 previously. In this case, AH will be 1. So simply it will be AH will be 1 and AL will also be 1. Clear? And carry flag is set because if we add 9, if we add 6 B with 6, so we need to have a carry. That is why we have changed it, changed the value of the carry flag, right? In both the cases, it clears the high nibble of AL. High nibble of AL, that means AL. If AL is, for example, 2B, then after AAA, this will be simply 0B. 0B plus 6, that means it's 1 and 1. So in every single case, this higher nibble of AL will be 0. Clears the high nibble. Next is sky adjust after subtraction. Sky adjust after subtraction is when we need to check whether it is greater than 9 or less than 9. If it is greater than 9, then simply we'll subtract the 6, and if it is greater than 9f, then we need not to change we change basically the carry flag from 1 to become 0. In both the cases, high nibble of AL will be 0 again. So if, for example, MOV AX 202FF, that means AH will be 02 and AL, that will be 0 FF. If we give the command AAS, then AH will be 01. Why? AH will be 01 because it is decremented by 1. So 2 minus 1, that will be 1. And what about this? This is FF. This is FF. That means we need to subtract 6. And when we subtract 6, F is that is 15 minus 6. That means it is 9. and since it clears the high nibble, that means this F9 will become 09. Clear? AAD, that means ASCII adjust before division. ASCII adjust before division, that means we will be having the value of AL that is calculated by simply AH into 10 plus AL. For example, we have 3 in AH, we have 3 in AH and 2 in AL. Then after AAD, this AX will be 32 because it is 3, this 3 into 10 plus 2, that means 32. So it will become 32 and 32 will be considered as a hexadecimal number now. And if we want to divide, then move CL comma 8, that means we want to divide 32 from 8, and 32 will be divided by 8. The result will be 0, that is a remainder, that is 0 will be stored in AH as in the previous example of divide, and the quotient will be stored in AL, that means 32 divided by 8, that is 4. This 32 is not exactly the hexadecimal number, it is basically a BCD number. 32 divided by 8, then only the answer will be 4, otherwise it's not. So this AAD command changes 32 into 32 in such a way that these 3 and 2 combination will be considered as a BCD number, not an hexadecimal number. The last command is AAM, ASCII adjust after multiplication. So algorithm is simply AL divided by 10. AL divided by 10, that means we divide it by 10. In other words, let's take an example. If we want to multiply 0.5 with 0.9, then the result will be 45. So 5 into 9, that will be 45. But if we multiply CL with AL, then the result will come as 2D and AH will be 0. And that 2D will be basically 45 of 45 decimal is nothing but the 2D in hexadecimal. So if we see this after this AAD command, what we get is 0.5 separated and 0.4 separated. So 0.5 will be AL and 0.4 will be AH. Clear? Thank you.